And we are live. Hello Internet. Today I am, first of all, drunk. Two, trying to debug pip performance problems. This will not be regular video, as I have no script, no plan, nothing, except for the fact that I'm disappointed with some dependency resolution time, and I have some wine here in my cup, and some wine already circulating in my blood. So apart from that, anything else can go here in this stream. Feel free to stay here and watch me maybe embarrass myself publicly, maybe not. We'll see. And apart from that, hopefully you will have fun with me, and we'll try to maybe fix some problems with how pip resolves dependencies. Or, well, not exactly pip. As you will see, this is actually something that's rooted within one of pip's dependencies, which are well vendored in, but we are going to try to do a root cause analysis of like where the performance problems lie and actually try to cache them. And who knows if we'll have a solution or not. Join me and we'll find out together. Cheers. So, we can now go first of all to actually clone pip itself. So this is going to be in the Python packaging authority slash pip. That's going to be our GitHub that we're going to clone. And within that, we are going to, first of all, by the way, I have pre-prepared test case repository with nothing really interesting. All we have here is, if we'll actually cat the requirements, that's not going to be a lot of requirements. That's going to be some, oh, actually, you know what? Let's actually cat the project. So we have Fast API, UVcorn, Async PG, Pydantic, SQL Alchemy. Really nothing special, like very slim, very small. And still, if we go with and actually try to regenerate the log file, it takes like a decent amount of seconds. And this is what we are planning to maybe fix today. This is not actually a problem with Rye, and we can show that by actually trying and running this with a debug version of Rye, which I have pre-compiled. And that will actually run this synchronization and will give us a profile. And as we can see, a lot of the time is spent here in the doResolve function, which calls the resolve lib code. And if we look a bit deeper into whatever is happening here, first of all, we've got some sub-process, which is basically the build time of some dependencies. But we also spend a lot of time here in SSL land, which basically means that we are making two places, two call sites that we can probably optimize by caching. If we look a little bit deeper, we can see here we've got add to criteria and we've got attempt to pin criterion. These two functions are probably the place we want to go to, because these are the places where basically if we look at the odds, we can probably already guess what, we can already cache the response once, and then we can load that up and only look at the cached result without actually going to the internet the next time that we run this function. Okay, so now that we've got ourselves, first of all, profiling information, we do actually have like good suspects here in the resolver. We can try and figure out what we can try and figure out how to solve that. By the way, if you can't see what's going on here, let me zoom in and I will just show the fact that here SSL is spending a long time, here SSL is spending a long time. Sadly, the flame graph isn't super friendly to, well, using high zoom mode, but you can believe me here that we've got sockets here, we've got SSL here, and basically everywhere we see candidates something, or we can probably see it's either networking or building something. Here, as you can see, this is building like an source distribution. This is not the place we like to debug. This is probably harder to debug, and networking is basically wasting most of our time. So now that we've got a rough idea of where to find things, let's actually figure out what we can do. So let's clone pip and actually try to make that work. So git clone for slash pip, pipa slash pip. And let's open that in PyCharm once it's cloned. Actually, you know what? First of all, Python 3.11 -m virtual env, and let's activate that. And it says no module named virtual env. Oh, as I apparently I have forgotten to deactivate the previous virtual env. So Python 3.11 virtual env venv, and let's activate that. Okay, so we are now within a virtual environment, and now we can actually run PyCharm and figure out what we can do in this code. Salute. So let's configure our interpreter. Existing, well, that's not the right one. So which Python pb copy. And we are now configured. By the way, PyCharm is kind of nice in most things, but managing toolchains here is not nice. So if we look at the stack frames, we can see a lot of time is wasted on attempt to pin criterion and on add to criteria. So these functions are within resolve-lib. We are, in order for us to actually submit a patch, we can probably try and actually fork not pip but resolve-lib, but we will try to debug here where the code is vendored in, and then once we maybe have a working thing, then let's actually try and like upstream that. So where we are in resolve-lib, and everything that we probably do is within either resolvers or within providers. By the way, PYI does not do anything. Like this is just typing metadata, which is obviously important, but right now it does not interest us at all. And what do we have here? So our resolver, which as we can see here in the stack frame, we go to resolver struct found candidates. This is where we actually spend a lot of our time. So resolvers pi 397. So let's just go to that line exactly. 397. And that is add to criteria, as we've seen right here. Right? We zoom out, we get probably more detail. Where is it? Yeah, add to criteria. So we are in add to criteria itself. By the way, I see this, it fails to actually display things correctly. So that might be problematic, and we might actually want to go to resolve-lib itself and not to the cloned pip file. So let's actually investigate that through resolve-lib itself. So let's just clone that a little shortly. Resolve-lib. And in our terminal, let's just git clone resolve-lib. And we now can investigate that correctly, probably. By the way, of course, we'll have a little bit of drift between the version of resolve-lib and pip that we're using externally with the problem with the program we're debugging and the actual lines that we have here on the main branch of pip or resolve-lib. So where are we right now? We are in this place. So we go to resolvers and let's just ignore all of this crap, all of these warnings and messages and notifications from my IDE, which are obviously unuseful. And what do we have here? We've got resolution. This is the thing that actually does the resolution. It gets a provider and a reporter and actually does the add to criteria function, which is the place where we basically report that we're adding a new requirement, we're doing some identification, and we're actually doing the algorithm. So this is probably the place to actually cache things. And this is where we'll try and figure out where do we want to actually call this provider correctly, and or maybe wrap our calls with our cache, and then we'll figure out if things are actually working faster now that we're doing something new. So first of all, identify requirement seems like a thing that can be cached because it's a pure function. Like the provider does not know anything else apart from this requirement. So this call probably is cacheable, given that we are backtracking and calling the same requirement, calling this function with the same requirement more than once. So we can try and investigate that and actually figure out. So we can, first of all, add a counter and just count the number of times we're seeing the same requirement visiting this criteria. I wonder what would be the easiest way to actually integrate that. So let me think for a minute. So resolve it, this would be a nice way to debug and test this one specifically. But if we actually use pip, we could try to install that into our virtual environment and then actually use our new pip with the vendor changes. So probably this one. So let's try and count the number of times we see the same requirement. So let's go to basically the initialization of self here. And we can just add self counter. Let's call that requirement counter. And let's just use, was it collections counter? I think that's the right way to initialize that. And now we can use that wherever we see fit. So self why do I not see that requirement counter? That's interesting. So interesting. So let's just use that and not worry about the fact that it's not auto-completing, because auto-completion is overrated in these scenarios. So let's just do that. And let maybe Copilot, will you please just help me with the API of counter without me needing to Google it? So collections counter. So we are initializing the counter, and we can increment that how? Elements, subtract total from keys, update. Counter C plus D, that's not interesting. D and D. How do we just increment the counter? Why don't we have like the, well, like a plus plus basically? Subclass with for counting hashable objects. Yeah. So C bacon 0. Elements most common, subtract total from keys update. So do we just update everything every time? Elements are counted from an iterable. So and the iterable is expected to be a sequence of elements, not a sequence of key value pairs. Okay, so probably let's just see the usage of the update method. Update. That's like probably the right thing to use. So I'm wondering why aren't they not? So from keys, this class method is not implemented for counter. Okay, that's good to know. Okay, so basically just let's update that with our requirement. So as they've said, this is not an actual key value pairs. This is just a sequence of elements, and that will actually use that. I think a counter is more a set, like it's not really a set, but basically it's a multi-set. It stores the amount of times an item was inserted into the set using a dictionary, but basically it's more of a set than an actual dictionary. Anyhow, we can move on. Hopefully this works. We've got our reporter. We basically have our requirement here. So let's try and make this work. And let's just, when we exit the resolution phase, which is probably, let's figure out where's the end of the resolution phase. So yeah, here we can, I just want to basically log whatever the actual what's the actual counter here? Like what are the actual values, and we'll see how many times we have duplicated the work here, and this will allow us to know whether it's a good place to actually insert some caching, if any. But only after the resolution, because, well, we need to first resolve and then actually figure this out. And in order for us to find that easily, you know what? We can actually do better. So we've got our result, which is just going to be this value, and we're just going to breakpoint here, and that means we will definitely not miss that. Unlike logging and things that go to maybe std out, maybe not. We'll figure this out. Print. So that's going to be, let's call that visited. So that's going to be duplicate lookups. Sure, whatever. Let Copilot format that however it likes. Let's try and actually install that and figure out what we can actually try and do. So let's cd back into pip, and here we've got, do we got here virtual environment? Yes, we do. Oh, I see that warp is basically breaking our prompt, and it's like putting the virtual environment prompt not in the same line on as our shell. Well, at some point I will try and figure out how to unfuck warp's prompt handling. One other day. So pip install -e this place. Okay, so we have now installed our own editable pip version with our edits right here. And we can now try and open a new directory. Let's go to our test case, which is our weird directory here. And we can activate our virtual environment here. Do we not have that? Oh, yes, we do, but it's on .vnv. Yeah, so how would we install pip here correctly? So, Okay, this is actually a tricky bit because, well, Rai abstracts the use of pip from us. So let me ponder on how we can actually use our newly uh, our new pip, basically. First of all, let's just Rai sync with dash dash verbose or something. And we'll see maybe some logging, and we'll see where is our pip actually running from, maybe. So nothing super special here. This is a lot of logs, but nothing very informative. Packaging, that's not it. Generating log file, using cached, blah, 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 blah. A lot of stuff is cached. And it says using pip from var folder. Temp. Interesting. I'm wondering what happened there in order to make pip run from a temporary folder. That is like magic that Rai does. So let's actually try and figure out what does it do, because, well, we need to figure this out. So we've got pip tools themselves, which have probably their own pip installation right here. So, that means we can probably, if we go here, we've got bin activate. Amazing. So within the virtual environment of pip tools, which is the virtual end that actually runs everything, we can try and, okay, let's save this path, deactivate our own venv, deactivate. Yeah, so no virtual environment, and we can now run this one. So now we are modifying the pip tools directory, the pip tools virtual env, and we can try now to run, first of all, Python. Which Python? That is the correct version of Python. Okay, so python-m pip install. And we want to probably install our own pip. So that's going to be cd back into pip and this one. So editable. Okay, so we have now overridden Rai's pip implementation with ours, and it's editable, which means every time we edit pip files, we will actually see our newly edited changes, and that will help us maybe run things correctly. So first of all, let's now cd back into our test case repository and run sync -- verbose. And it says failed to generate log file, could not write production log file for object. Interesting. So first of all, it says pip subprocess to install exited with. Okay, so we have fucked up. That's good, because that means that I have actually. Ooh, BDB quit. Okay, so we have basically met our breakpoint, which is a good thing. But before that, we see that we have seen counter 111111111. Interesting. And that is just packaging, hatchling, pluggy. So these are not things that are actually using the requirements of directory, but other things. Basically, okay, so we can just try to, first of all, let's eliminate this one. And maybe let's actually try to print our results. So let's import pprint. So pprint of our results. And let's remove that. And that now is going to maybe show us how many times we have visited the same space, same place. Let's figure it out. Maybe we don't actually need the verbose flag. It might just show up no matter what. Okay, so it definitely did. So we are visiting a lot of things exactly once. So that is probably not a good place to go to because, well, everything is basically visited exactly once. But maybe let's just figure this out, because if we see Fast API more than once, then that means we are visiting the same place more than once. Well, so that is actually a thing. As you can see, we've got ourselves the same requirement, which is like under 105 and then greater equals than to 104. So the requirements by themselves are not good enough in order to basically cache things, because we've got 104.1. Interesting. First of all, I don't know if you've seen this, but if we highlight this part, we've got the exact same requirement, but it is considered a different one according to the counter, which means that our counter is not doing what we expect it to, because probably specify requirement does not implement the dunder equals method correctly, or dunder hash or something. So we need to basically improve our counting mechanisms, and that will help us to see how many times we've done duplicate things, duplicate work. So back to our counter. So first of all, that's a list. That's okay, but how would we make this exactly countable? Add to criteria, requirement, state criteria. Maybe let's dive into how requirements are exactly specified, and let's try to hash that correctly. So, requirement. Where are all the type hints? That's really I'm really missing the type hints. Resolver, abstract resolver. RT resolvers. Yeah, so requirement information, that's going to be a tuple of, well, no, that's information. That's not the requirement itself. Where's the requirement? RT. That's generic. That's not good. Um, so this is a tuple that accepts a generic. Let's see if where is this initialized with what. And that requirement is add to criteria. Well, basically back in a cycle. I'm looking for the requirement class, not the requirement information class. Provider, maybe? Class requirement. Oh, that's the one. So, this has project name. This is different from name if the requirements contains extras. So probably name is the right one. is satisfied by. Okay, so let's just use the name as our counter instead of the actual what's its name? Instead of the actual object. So dot name. Let's rerun that and let's figure out if we've got a better view of our visited dependencies. So that name, as we can see, now we've got some more information, but we have lost version information, which means that if we visit different versions of the same package, which definitely cannot be cached, then we won't see that here. So we probably need something like a tuple of requirement.name, comma, something, and maybe version. And that's obviously not enough because, well, first of all, there is no attribute called version. Specify requirement. So requirement, where was that? Class requirement. So we've got satisfied by candidate. No candidate lookup format for error. Subclass should override. Interesting. Maybe just using the Thunder Ripper would actually make this work. So let's actually do that. So our requirement itself is going to be, let's go to counter. This one, yeah, here. So let's just use literally wrapper of requirement and try sync. Okay, so now we know that how many times we've visited stuff. That is very good. And by the way, now we can see things like we also visit nodes like requires Python. Interesting. I was not aware this is something that would happen even. I don't think this is like ever supported like the 3.7 thing. Okay, so that's a good start. By the way, like we can basically we can obviously add more like crazy stuff by adding more dependencies. So we can just add, I don't know, GCP AIO storage or something. Yeah, so let's just add that as another requirement and like gRPC and I don't know. Basically, let's just add a lot of crap and that would make things harder for the solver and then we can actually see um, more duplicate work. That would make it easier to see where we should actually like pin the cache. So let's just try sync again and we'll maybe see more stuff. This is going to be skewed by time because right now probably these packages are not installed, so it might actually download stuff, but we are okay with that. What actually took time is not this one, but this solving. So as you can see, more stuff has appeared, like less than 4, greater than 3.8. That was not here before. And we have visited the greater than 3.7 more than once. So each time we see this, we basically need to probably cache that. or things like specifier without extra requirements, UV colon, blah, 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 blah. Yeah, okay, so probably there's some caching to be done here, basically. I wonder how much time do we actually spend here? Um, how would we know that easily? Let's think about that. Um, mm, mm, mm. We can run like cprofile and not directly use the not use the flame graphs, but actually like look at the actual time and not like the merge time of each stack frame. But you know what? Let's just move on. So we know that we've got here mostly hashable requirement thing, and we can, if we hash it correctly, we can basically cache this response without us needing to go into networking. I wonder if the provider itself is actually doing any caching on its side. Because if it does, then that means we can basically call it a day on this end. So let's actually figure out if this provider is doing anything smart. First of all, let's just print once the type of the provider. What is the good place to do that? Probably in the dunder init. So yeah, print self p and also probably type self p. Yeah, that's good enough. That's going to be more than enough for us to actually figure out where does this. Yeah, okay. So it's pip provider. And if we look for pip provider, we see that here. And does this do any caching on its end? There is no word of caching here. So we could add that on the resolve lib end or on the actual provider end here. That's going to be another question of like where does this need to sit? On the algorithmic side of the resolver, which is like the backtracking thing, or on the provider itself. So resolution, resolve lib, provider. That's on the internal side. Okay. So I'd say, by the way, that probably leaving the leaving resolve lib alone and actually debugging the issue on the internal side of pip would be probably the correct way to do this, because adding like other packages that depend on pip probably have their own like maybe caching mechanisms. I don't know. So maybe trying to figure this out is going to be better on the pip side. So let's zoom out a little bit just so I'll see a little bit more context. No caching here. Pip provider. Okay, so we've got some factories identify. So identify is basically just requirements candidate or name. Okay, so identify does not do anything fancy, so we don't need to cache any of that at all. If we go back to resolvers on this side, first of all, oh, sorry, shit. Pip provider. So, identify. Yeah, so this is basically not worth doing any caching for that because this is a really simple function call. But criteria.get identifier. That might be interesting. So criteria get. What is this criteria object? That's going to be our next thing. So criteria is self-state criteria copy. And what is dot state? Is state just like a regular dict or anything special? Self state equals does not equal anything at any point. That's interesting. Who initializes the state? So we've got states, but where's the state itself? So it's a property. Interesting. So that's going to be the latest state. Raise attribute error state. So the usage of self.state is always just looking at the latest version of any states that are given. But that means that is it only right? No, it's not right only. So let's actually look at the algorithm. Um, so we've got resolve. How does this look like? So first of all, if states, then already resolved. That's interesting. So we report starting, and the state is now initialized with a root state of, well, mapping all the dict with nothing in it, criteria empty dictionary, and backtrace causes nothing. For requirement in requirements, we add that into the criteria, and we accept an error of a requirement conflict, and we raise a resolution impossible error. That's good. And then we push new state, which is a thing that we need to really see what's going on here. The root state is saved as a sentinel, so the first ever pin can have something to backtrack to if it fails. The root state is basically pinning the virtual root package in the graph. Okay. And let's actually look at the algorithm here. So for okay, so we're basically retrying anything for I don't know, max rounds, which is probably like basically infinity until we satisfy all requirements. So we report starting round, and then it says unsatisfied names, and then it says we're iterating over our criterias. Is current pin okay? So we are if okay. So this is all the unsatisfied packages. And if we have no unsatisfied packages, we basically end and return the state. If we do have one of them, then we are solidifying them into a set of satisfied names. Oh, so okay, so we're okay. These are the satisfied ones. These are the unsatisfied ones. We take the most preferred. How do we know what's the preference? Get preference. Interesting. Okay, so apparently we can wait, like have some weight into some packages. I'm not sure how and why we can actually do that, but sure, whatever. Um, if failure cases. Let's figure this out. So R, resolving conflicts, back jump causes. So back jump is probably like our backtracking. That's how we actually backtrack things. So let's actually look at back jump and figure this out. So when we enter here, the stack is likely like this. State Z, Y, X. Earlier states are irrelevant. No pins worked for Z, so it does not have to pin. We want to reset state Y to unpinned and pin another candidate. State X holds what state Y was before the pin, but does not have incompatibility information gathered in state Y. Each iteration of the loop will identify Z. The incompatibility is not always caused by the latest state. For example, given three requirements, A, B, and C with dependencies A1, B2, C1, where A blah, 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 A1 and B1 are incompatible. The last state might be related to C, so we want to discard the previous state. So we discard Z. Um, it's called why, but remember it's an incompatibility information gathered previously, and the failure we're dealing with right now. Push the new state y tag based on x. Apply the incompatibility information from y to y tag, and if this causes y tag to conflict, then we need to backtrack again, making y tag the new z and go back to step 2. If the incompatibilities apply cleanly, we can end the backtracking. Okay, so let's actually see that in code, or you know what, we don't have to. But basically, this is the place where we actually try to do this resolution thing. And the only thing that's important is like, where do we actually do the extraneous networking? So let's figure that out by looking at the profile a little bit more, and we'll figure this out in a minute. So first of all, as we can say, it's add to criteria. Then we dunder bool on structs pi. So where is this dunder bool thing actually running? So found candidates. So let's actually look into found candidates. Def found candidates. Why can't I see it here? Is it in the whole project? Resolve lib, found candidates. Oh, so that's the name of the module. Interesting. So it's underscore it's a built. Yeah. So where is this called? This is called in exactly one place? No, that's probably not correct. Yes, it is. Interesting. So, and where does this under iter get called? This is found candidates the class. Yeah, this is where code intelligence would actually be useful, because iterating over something, that means we are looking for a for loop. But this is a generator expression, and that is on structs pi. So let's actually go for structs pi. That's going to be a file struct.py in resolve lib, and we have dunder bool. Yes, we do. And we can see here that what we've got is 156. So bool sequence. And that thing actually needs to look up within the sequence on the truthiness of that sequence. But that sequence is probably something fancy, because apparently if we actually look at that, that actually does like work, and not this actually calls like more and more functions. So found candidates bool. Bool. Yeah, and this one, it says if self prefers installed and installed. And this one, these two are, well, are these also booleans? No, wait. 155. Any self. What the hell? Yeah, so this is the anything, the any call. And that's 143. That's going to be probably an iter method. Yeah. So, and within here, we're doing a lot of work. Interesting. So for the address of, like, ID is the basically the identity of the object. So for what the hell is that? Very, very peculiar. So iter index candidates info. candidate infos. So which one of them would that be? Factory 284. Um, line 284. Find best candidates. Is that correct? Yeah, it is. This is all very weird that like the line of the function is always denoted after the actual thing. But yeah, sure, whatever. I'm not going to like complain about like PySpy. It's a really great profiler right now. Anyhow, yeah, so find best candidates actually does probably a lot of work. First of all, I can see it's already cached. That's very interesting. So find best candidates is already cached. That means that every time we walk into it, the cache is not populated. And why is that? Wait. Ooh, interesting. So first of all, self is part of the cache key, which basically means that every new instance of package finder is going to have its own cache and this leaks memory forever, but sure. Um, so how does that work? Like who initializes package finder? And if that is actually like the problem where we initialize it more than once, then that is going to actually be really helpful. So finder is actually initialized once here. So factory, do we see this factory here? Factory, yeah. So factory pi find iter index candidate infos. Find best candidates, find all candidates. Wait, finder, package finder, is that right? Yeah, okay, and that is within find all and find best. So let's just go with, well, find all. And we put all of our time within find best, is that right? Or is it the other way around? So it's find best, find all, page candidates. So let's actually look within page candidates. Is it a function? What is it? So it's within sources. Interesting. Okay, so let's figure this out. It's somewhere within find all that we actually call into page candidates, and that is actually not cached correctly. So find all, and that says here we are collecting sources. Let's just actually deep dive into that. So here we've got page candidate process project URL. Process project URL. So that is a callable. Interesting. And we're passing that into a partial. Then it says candidates from page. And who actually runs this? So collect sources, probably what's that? Build source. And it's per page. So from self-link. Interesting. So I think this is actually maybe a good place to maybe cache. Maybe let's try to maybe cache that. So if we actually look into this thing, where is that partial one? Yeah, so candidates from page. Let's actually add a cache to this function and let's figure out whether this actually runs correctly. So first of all, like this can obviously be cached because, well, it's a link evaluator, which is just a function. Probably it only depends on probably the string. So nothing fancy or interesting here. Okay, so first of all, this is all cached. So that means we are only seeing the actual not cached one. Maybe we want to use, well, let's actually try and figure this out by like, I don't know, let's actually restore this cache really, really in a dirty way from, well, from disk, basically. Let's try to skip all the networking. So that is running right here. Is there a way to actually inject like cache into functools? So functools. Actually, let's just look at the sources. We can probably figure this out easily. So by default, it's 128 and it's typed false. And it says users allowed to access blah 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 blah. Users should only access LRU through its public API, cache info, cache clear, and F wrapped. Where's the actual storage? LRU cache wrapper. Max size. Where's the actual cache? Cache get. So that is some like where's the actual, okay, so that's the cache. What's the easiest way to access this cache? Interesting. So all of this is like within a closure, so quite hard to actually go get into the cache itself. Not impossible, but I mean, probably not the best nice thing to like, not the nicest thing to actually try to figure out how to do. That's really nice of them, but sure. Let's actually print the cache info. I'm quite curious now. Are we actually looking at a really hot section or not? Where is this called? Right here. So self find all cache info. Print that. Let's just have some find all cache. By the way, this probably would have been a lot faster if I would have actually known like where the problem exactly lies, but it is really hard to actually know that. But as we can see, a lot of misses, some hits. Um, but this is the interesting thing. As you can see, we are doing duplicate work between runs. And just so we will also have a little bit of info about like how long are we actually spending here. Um, let's actually attach one more thing to this, which is like, and I know it's like crazy to do this way, but yeah, so start is going to be time perf counter, and then let's just actually use nanoseconds. So we'll have like the actually accurate clock. And so we've got perf counter, and we've got end, which is also a perf counter. And we can, do we have a logger here? Oh, if we have a logger, that's really nice. But actually, let's make that info because we want to see that. But also, logger info. Yeah, let's run that again and let's figure out. And it says failed. Why does it fail? And it says logging, not all arguments. What? Say what now? Yeah, that's important. And this does not actually print it out, so that's not good for us. If we error this, then will it be printed? Just so we'll have a little bit of info. Yeah, awesome. I don't care about this, but okay, so okay, we are spending actual time on networking. Like if we sum this up, this might be actually the time we're actually spending doing network stuff, as we actually know, because if we look at, well, the profile, we know that we're spending time here. So that's the sum of the time that we're actually seeing here. So let's figure this out, shall we? This might be just the thing that we need, like we need to basically try and maybe put this cache on disk and not only on, like not only in memory, basically. If we go back a little bit higher in the stack, we see that most time is spent here. A little bit more time is spent here in package finder, but that seems like way less relevant. And here we have a little bit of more time that we actually might try to make work, like make this work. What else do we have here? What is this? This is pi parsing. No, we're not going to debug pi parsing. That's crazy. Yeah, okay. I think we are in a good place. Like I think trying to make this work might actually be the thing. By the way, I see that they are trying to cache some stuff. So as you can see here, they already got caching somewhere here within the middle. I now lost the stack trace. Let's just look for uh, cache. Yeah, so they do have cache control right here. So if they already have cache control within requests, why is it failing? Bum, bum, bum. So index collector. So let's figure this out. Apparently, like this is cached. We could try and persist this cache. So let's actually add a to do here. So to do persist cache between runs. Yeah, that should do a lot of work for us. By the way, we should probably not use PyCharm's horrible built-in formatter and just use black tools. Black let's just go with binary, our own uncode format. Yeah, and yeah, this should now be like as good as possible, like as best as possible with whatever it's doing. Never mind. Anyhow, I'm blabbering on because I'm drunk. Um, so we know we're spending time here, and we've got some cache hits and cache misses, which means that this LRU cache could be better utilized if we actually persisted between runs, and that would, if we saved it to disk and like reload that, that might actually be useful. Now that we know that, we can try and maybe figure out the root cause. And as we've seen, we've got here our what is it? Cache control adapter, which is called here somewhere within the index collector. So somewhere here in this stack, we can try and figure this out by actually implementing here just making this cache better. So but we'll figure this out in a minute. So cache control adapter. So adapter.py, and we've got a lot of cache here, caching. Okay, so that's going to be an HTTP cache. Invalidating methods, put, patch, delete. Okay, that's very good. And where's this used? So this one is used within wrapper pi. And we will not be seeing wrapper pi within our stack trace because it's probably just wrapping some object and then giving it back to some other place to actually use the thing. So cache control. So this is defining cache control, and who's calling it? So let's just look within Pi files. And actually, let's just use case sensitive search. And let's add boundaries. So cache control done the init, and then network cache. Seems like the place to be at. If this assumption is not true, the cache control issue will need to be fixed. Safe file cache. Okay, seems like a good place to start. But actually, you know what? Let's just browse on with our history of boundary, and that's going to be defined, and no one's calling this function. Interesting. So we are importing cache control, and we are exporting that again. And is nobody actually trying to import that? So from cache control adapter, people are importing that. No, they are not. Is it not in a Pi file for some reason? Or is it just not used? But we've seen that. Cache control adapter 76. So cache control adapter, line 76. So this send method is definitely called by something. And we do have an HTTP adapter. Interesting. Okay, so we are sending the request if it's not probably stalled. Okay, send a request. Use the request information to see if it exists in the cache and cache the response if we need to and can. So if request method in cacheable, try cache response cache request. Yeah, so that is going to be the thing where we actually look up in the cache. No cache, max age, blah 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 blah. Case insensitive dict. Apparently, that's a thing. I was not aware it's not something that we have. I mean, it's nice, but I hope this is like built in C and not in Python land, but what do I know? Class. Okay, this is definitely something built within Python. Oh, that's quite the shame. I mean, works, but yeah, could be better. Okay, so we've got headers. That's not interesting. Yeah, so we do have an HTTP cache, and and the cache claims these requests do not exist here for some god awful reason. Um, hmm. So within this send method, where is the actual cache? This is the thing that I'm actually interested in. So try accept zlibel cache response none. If it's truthy, then we can build a response. So yeah, we need to figure out where does the cache actually live. Load from cache. Self cache get. And this cache is dictionary cache or another cache. Interesting. So cache controller. Um, so who actually instantiates this class? An interface to see if a request should be cached or not. So command adapter cache controller. Who instantiates that? So controller class. Or cache controller. So controller factory. Mm-mm. So this is usually a dictionary cache, and let's actually cache etags self cache. Oh, that's a thing. Okay, so cache control adapter. This is dictionary cache or this cache, and this base cache, which has get set delete close. Um, who initializes that? So that's a dictionary cache instead of a disk cache. I would definitely prefer a disk cache because, well, we'd want something that's like not tampered with, basically. Not, I mean, tamperable, but like we can guess that it's safe. Um, so cache control adapter, dict cache. And get session is done exactly once on the command of pip. So, do we have other caches that are not dict? We've got base, we've got dict, we've got separate body base cache, and that's it. Hmm. So how would we have trusted disk cache without like how could we trust that this cache is actually controlled by us the whole time, but it is persisted between runs? By the way, we can definitely you can probably see that this cache is getting hammered by actually just printing um which key is actually used. Um, you know what? Let's actually only get that if it's none. So let's just extract this, all of this result. Yeah, and if result is print, yeah, so this is going to be a cache hit basically. So let's just sync this very quickly. And we, for some reason, we don't see anything. That's interesting. Ooh, why are we not seeing anything? Logging error, everything, and that's going to be command S, yeah, this thing. So this cache is not being hit or utilized at all. Interesting. I would assume this cache would actually be very much in action because we've seen it initialized in a lot of places. So why is it not being used? Do we see it actually being set? Let's actually log that quite quickly. Um, I might be I'm suspecting this is not being used. So basic config and then log level logging debug and logger. Yeah, okay. This is going to be horrible, but yeah, okay. So we've got some more information. Verbose. But still the cache is not being utilized. So we are definitely seeing the fact that we are like this file is being imported but not being used. So that is very curiouser basically. So we've got ourselves our cache, and this is basically being initialized a lot of times. By the way, we can actually see how many times this cache is being initialized by saying dict cache init. And let's run that quickly, and we'll see dict cache. Very interesting. Why am I not seeing that at all? Is this not working as expected? Logger error cache pi. So cache pi is here. So this is definitely being imported, and dict cache, which is being used in a lot of places, is not actually being used. If we are seeing it here hard-coded, then it says cache control adapter. And if we look into this one, let's actually log that. So logging debug cache controller send. And it says, yeah, failed to import logging. Send. I am very confused. So logger, get logging, and logger. Where's that? Build response? No, here. So logger info. Yeah, okay. Let's run that quickly. So these are not being printed at all. Let's actually run that with PySpy just to be sure. It says requires root, and they are correct. And let's just give that our root permission for the profiler. And here we've got another profile. Let's actually look into it. So CPython, pip compile resolver, backtracking, no annotate, blah 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 blah. And it says package finder collector. Where's the cache? No cache. Interesting. Can't seem to find the cache. Okay, so we do see the cache. So cache control adapter line 81. We are within adapter line 81. So this one is definitely being called. Response, super response. So HTTP adapter. Class. HTTP adapter, and it says and that's our next line, right? 486. 486, and that is URL open, which is probably what we've seen here in the profile. So yeah. So this one should definitely be logged. So let's log that. Do we have any kind of logger here? Self log? No. Any like report, anything like that? Okay, so just 486. And let's just add here logger dot info, and Copilot is definitely confused, but sure. That it? No, we probably have a lot more to actually figure out. So let's just go with request dot URL timeout. Sure, whatever. And let's just create a logger. We're basically hacking away, and I'm not sure like what are we aiming for exactly yet, but hopefully we'll find something. So for some reason, this is basically not being reported into what's it called? Sorry, my mind is melting. Well, and I'm out of wine, so I won't be thinking any smarter from this point on. Yeah, so I'm failing to log stuff, which is kind of annoying. But we are definitely using this code because if I let's just actually do a sanity check. So logger instead of logger, that's actually just one div zero everything here. That should fuck up everything. Yeah, and basically things exploded with one div zero, and we can see zero division error. So we're definitely using our own code here, which means that we need to somehow write into sys std out correctly. Let's just actually use, well, print. Come on, Copilot. I don't have all day. Request. Yeah, that's bad. Let's just f string that and go something. Let's just log anything at this point. I will do. I'm okay with anything. Okay, so prints work, logging does not. Okay, I can work with that. So now that we have that information, let's actually go back to our cache and let's leave this adapter alone. So we've got, let's go back to the latest profile. So let's just run that without like extraneous prints. So we do have cache control at some point here. Yeah, so adapter, cache control adapter line 80. So adapter line 80. And that's the one. But that means we have failed this cache request. So first of all, let's just be really, really basically let's be terrible. A prepared request, is that cacheable by itself? Class prepared request. That's going to be a lot of stuff. Does it have dunder equal? It does not. But it does have a dunder wrapper. That does not seem good enough. basically we need to ask the cache whether it's good or not, and let's try to, okay, load from cache, that's the one. So, oh, right, we were here in the dictionary cache, and instead of logging, let's just print everything. So print. And also here we can print. So this one basically does not really work yet. So no logo at all. And this actually proves us that this is not in use, because we have just broken this with like basically a namer, and this code is dead. Okay, interesting. So since this dictionary cache is dead, and this one is actually not used, then what is actually being used here? So dictionary if cache is not none, else cache. And there another kind of cache here that we're missing, maybe? So we do have separate body base cache. And that's another base cache. No super calls. Let's figure this out. So we've got a file cache mixin, base cache, and this file cache mixin actually does some stuff. Do we use that file cache? Let's one div zero that out. Please crash. Give me something. No one's using that cache. That's not good. Okay, so no one's using this file cache mixin, not really. We are inheriting from it, but we are not using its dunder in it. I'm not sure. I'm confused. File cache mixin, and this one is hashed and code name, but this is a class method, a static method. Yeah, that's just sha. So we are not actually using that. We've got file cache, Redis cache. So there's a lot of cache implementations here, but none of them are used. I'm very, very confused. This is all still very, very much unintuitive, like what's going on here. So this cache control thing is not used. If we go back to our profile, page on candidates, package finder, collector. And then we just dive deep into a lot of shit, basically. So sources 134. That's probably a good place to go back to. Sources 134. page candidates from pages, and that's a thing that we initialize from this thing, which basically is handed out callable, yeah. So build source is handed out a partial, if I recall correctly. So collect sources. Yeah, so basically that's the only problem I have with like using partials, which is you're basically passing like the stack around without actually calling it yet. And it is very useful sometimes and very terrible in other times. So we've got find all candidates, which is cached on disk. And we've got this process project URL, which is definitely like this function is the one that's calling all this crazy stuff. And this one is like the fetch response is probably somewhere in our stack. Fetch, no fetch. Parse links, evaluate links. Where's the goddamn collector? So we've got package finder. That's in line 788. So this fetch response is actually returning us a get index content. Why is it not in the Okay, so we've got get index content here. So this is not cached correctly yet. So let's just dive into that. So we pass the URL and then we say a lot of stuff and then we say get simple response from that URL. And for some reason this is not doing well. Oh, by the way, let's try to say debug equals R. That definitely did not log verbosely. Um, So self-page candidates. How many times is this called? Times is this called? Let's just say page candidates. Think fancy. Let's just run that. Actually, yeah, no need for PySpy. Stopped. Control C pressed. That's all right. Yeah, I wanted to close that. So we don't need PySpy. We can just rsync everything, and this should also work. So page candidates is being hit a lot of times. And the question remains is this the same object every time? So let's actually add self. And that will let us know if this is actually being, if this is the same object, then probably this function. Okay, so this is not the same object. This is being called with a new object every time. So remote file source is not the same object. So that's an interesting thing to note. And remote file source. This is being initialized for every build source call. And candidates from page, that's going to be a callable that returns something from something. But it's the same callable regardless of like whatever that thing is. So that means that candidates from page itself might be the thing that we want to cache. So let's actually figure this out. If we go back to our stack trace, because I cannot memorize anything. So get page candidates. Sources 1, 3, 4, and above that it's package finder 8 to 8. So package finder, yeah, 8 to 8. That seems like we are on the right track. Yeah, this is basically chaining everything. So this is where we are actually spending our time instead of this where we actually instantiate the variable. But this is the thing. And this source is being built right now. So collect sources and candidate from page. So yeah, if we go back, that's the one. So let's actually try and wrap that with our functools partial, because this one seems to be the thing that we are actually aiming for. I'm not sure if link evaluator is cacheable, but it does not need to be because, well, this partial is actually okay. Yeah. Interesting. Make link evaluator. So let's actually add functools. LOU cache. This is going to return us the same link evaluator. And then we can try and use this same one. So with the same project name, we expect to get the same evaluator. And we can try and actually make the same partial. So let's just call that, I don't know, make candidates from page func. That is going to return, that's going to take a link evaluator and return us whatever that was called. So that was candidates from page. and we can just try and return this partial exactly. Oh, still no URL. So this one exactly. And this one is going to, we can cache that now. And that's either going to work or fail completely. So LIU cache that. And our function is obviously unfilled. So that's this one, yeah. And we can try and now self make this one with our link evaluator. And how would we cache this internally? Interesting. Because we would need, we want this function to be actually cached. Hmm. I mean, it's already cached by project name. So is this really a thing? Probably not. Yeah, I'm reverting this back a little bit. So how would we attack this? That's the spot where everything is basically we need to cache to disk. So let's just do it like super dirty. So let's actually self and let's actually use shelf. So shelf, and that's going to be our sudo db, and we'd want let's just do that. Yeah, cache db, whatever. Expected mutable mapping bytes got stir. That's not the way to do that. How would we want this to work? I forget how do we write this to disk? So we need to enter and close this somehow. We need to write this into like a file, right? Shelf Python. By the way, don't use shelf actually. Like this is a really terrible database. I mean, you need to trust that the file is not modified. So this is why you can't use that in production, but for just proof of concepts, it's okay. So shelf open file name. Okay, so we need to say shelf open file name. We don't initialize that internally. We actually use shelf open, and then that's going to be cache.db. So with shelf open as cache, we are going to try and actually run that. So if project name not in cache, then collected sources, else this thing. And oh, actually, the thing we're aiming for is not in this area, it is within another place. So whatever that is, we are going to actually try and not list things. So this source is coming from source page candidate. So collected sources. Okay, so that's the thing that we want to do. So with page cache. If project name in cache, then page candidates cache, blah, 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 blah. Of course, there are no integrity checks on this, so this is why this is dangerous. I mean, everyone can just basically do whatever they want with this file if they have right access to it. But otherwise, we've got that, and then we need to write that into the cache, and I think this is it. So now we can print cache hit for project name, and here we've got cache miss, and now we can try that here. So this is going to be a cache miss for a lot of stuff. And now in the next run, it's going to be a cache hit. So that was super quick, as you can see. And now if we run that again, this is going to be, oh, that's nice. Okay, so that actually worked. I don't know if you noticed that, but this actually was faster. We can time that with basically, I wonder if there were any cache hits for the same project. So the cache here was used exactly once for each project, but that means it was persisted between projects. So that's actually nice, but that means we're still not in the right place, but like persisting caches to disk actually works. So that's nice. We are now going to try and persist this one because, well, this is actually where all the work is being done. So yeah, this LRU cache is nice, but we'll try and maybe add like more. I wonder if there's any place to like any way to actually make this secure, basically. Um, Probably not, by the way, because I mean, any user level script that's running with the same privileges as this script can modify this cache. So I know why they would use only LRU and not like this cache. I wonder what does poetry do in order to make this work, because poetry is actually solving things faster than that, and they do have some kind of cache there. So, okay, so caching things to disk actually works. And by the way, we probably have like a cache db thing here, apparently. So let's remove that cache because we don't need it at this point. How would we do that correctly? Interesting. So we could try and maybe load somehow the uh hmm, I'm basically thinking out loud. Um so we've got an untrusted database on disk, and we'd like to load it and either trust it and use it or not trust it and do the networking ourselves. And this is terrible because, well, um, there's no way for us to do this correctly, I think. Um, I mean, any other malicious script that's running next to us is going to be able to modify this cache. This cache cannot be pickle, of course, because this is basically just an invitation for running arbitrary code on pip, which we cannot support. We can maybe use SQLite just because we have native support for that in Python, and that means we can ship that. But also, like, I can't believe like pip would accept any PR with SQLite. Um, so how would we actually do that? I wonder how do they actually implement wheel cache? Wheel cache. I know there's like wheel cache somewhere within this place. So wheel cache itself is going to be simple wheel cache and ephemeral wheel cache. And simple is going to have a cache directory and get cache path parts. Oh, actually, when you think about it, they do cache things to disk with HTTP. And how do they trust these? So trust. Um, so these must be trusted somehow. Um, how do you do the HTTP cache? HTTP cache. Hmm. That's super interesting. Like how do you have a trusted disk cache? Or you might be able to say like, never mind that. I just don't want to, like, if you want to purge the cache, that's on you, but whatever. So we can persist things a little bit. So if we look at the wheel cache, let's actually look at that, because I think this is a good reference point, because wheels are not like HTTP requests that are signed by a certificate, so you cannot like verify those certificates directly. So wheel cache, get cache deal for wheel cache. It says if cache available, then should cache. This is the cache deal. Otherwise, get ephemeral path for link. So what is should cache? Request editable, source deal, then false. Okay, so this is a good place to start. So we either use the link for the persistent cache or the ephemeral path for the cache. And if we look at the wheel cache itself, how does it work? So it says get path for link, get path ephemeral path for link. Then you can have get entry, which returns a link, and you can get a cache entry, which returns an optional cache entry. And you can probably set that. Record download origin. Let's see that. So we've got origin path exists, direct URL from JSON. Read path. Log warning. Could not read origin file, blah, 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 blah. And then we just write the text. Download info to JSON UTF-8. Seems all right. And that thing is used only here. That's good. And this one is with indent log. Okay, that's not interesting. Build. Um, who is using this build thing? So wheel. Okay, wait. So get cache dir from the wheel cache and the requirement, install requirement. And that thing is ran exactly once. Build wheels. Okay, so wheel cache is okay with storing crap on disk with no trust whatsoever. Like this wheel cache dot get, wherever that was, test cache, wheel cache, get cache entry. It says wheel cache dot get. And that thing is basically canonicalized name, get candidates, wheel, and this initialization probably does not do any security stuff. So raises invalid wheel file name. Yeah, I mean, this is not a bad thing. All it does is basically we're matching against the file name. And then we are extracting crap out of it. And secure, there's no like signature, cert, nothing whatsoever. So no security considerations that I'm aware of, which is surprising, but okay, let's roll with that. Um, Probably they assume just that, your machine isn't tampered with because, well, that's not their problem with anything that they save on disk. So if that is the case, then we could be a little bit more lenient with how we actually persist these things. We could look at where the wheel cache is actually stored. So we've got ourselves a wheel cache, which basically, okay, so this is a really good way to model things. So if basically pip uses the wheel cache wherever it wants without looking at stuff and actually like looking at no trust whatsoever, then I mean we can basically we can do that ourselves like whenever we want, wherever we want. So this resolve thing is just a pip provider. So um, yeah, so this resolver can this provider can be cached like wherever. That does not matter. Um, Resolve. No diff resolve here. Provider. What does this provider like? I find myself always going back to the docs. So our provider not doing anything fancy here. Structs resolve lib. Add to criteria. So bool struct. Bool found candidates. So found candidates is like probably a good place to go for that. So found candidates. This is a module, and within that we say under bool. Then we say any self, and that brings us to this iteration, and then it iterates over one of these, and it's, I don't remember which one. With inserted, with prepend, iter built. Iter built infos. And it says here, this is the dunder next. So this iterator of index candidate. Okay, so who actually get infos? So that's the actual callable. This get infos thing, who initialized this function? Found candidates. This is iter index infos. And that is not a generator, which means, or is it? Yield. Okay, so this is a generator. So this is the one that's actually doing the work. So find the best candidate. Yeah, is it this one? Yeah, find best candidate. That's the one that's wasting time. So find best candidate is getting a project name, a specifier, and hashes. Seems like a very hashable thing, if you ask me. Does it have any internal state that it depends on? Because it says find all candidates, which is fine. Then we print the cache info, and this is cached. So if that's cached, make candidate evaluator, which basically does not depend again on the result. Candidate preferences. Who said that? Is that the dunder init? Yeah, so that's not interesting. If we cache according to self, that's all right. And this find best candidate is already okay. So we do already have the R to do here. So how do we make this cacheable, like more cacheable, basically. So let's try and hook some kind of cache here more than like the wheel cache itself, because we already have our to-do, or our to-do is in somewhere else. It's in somewhere else. It's here. So that one. So init, and let's just have here our, let's just put here some disk cache, or sorry, optional disk cache. That's going to be none by default. And there is no disk cache, of course, and we are going to implement that in a minute. But we can now add cache here. And that cache is going to be this one. Actually, that's going to be base cache. That's not going to be anything. We're going to pass this cache here, but nothing else. And let's just verify that base cache is actually, yeah, it has get set delete close. Seems fine. And let's try and make this work. So let's pretend that we have a cache. Actually, you know what? This is going to be or picked cache, right? Because this is the base cache. So that seems to be fine. Okay, so we do have that, and we can now try to implement our, first of all, null cache, but no, let's actually do a disk cache. And that's going to be a base cache implementation, and we can try to override everything that we need. So first of all, a disk cache needs to know what kind of like the call site that it's used in. Because, well, unlike a dictionary cache that's scoped to, well, the instance of this cache is actually scoped to the disk. So we need to make sure everything's working. I wonder, how do we actually like use the file system cache? Like, yeah, so user data there, that's like a good thing to note. Dot cache, user cache there. How do we actually get that? So platform dis, user cache path, and where is it used? Is it used? Hope it is. Platform dis, vendor, platform APIs, user cache there, command option, cache there. Okay, that seems good. There's, yeah, okay, seems very, very useful. This is the CLI. So in our package finder, we definitely want like, let's just call that, let's actually use the disk cache directly, because that's like the magic stuff. And this cache needs to have a directory. So this is going to be something like the CLI options. So app deals, user disk cache, pip, app name, user cache. Let's actually look at that. Okay, so Python egg cache. Okay, that's a good reference. So what it does, it basically instantiates platform deals, and then it uses that, and it says app name, blah 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 blah. So, and platform deals is just, that's the module. Okay, so we can basically use that directly. So we don't need to do anything apart from like giving that a name. And that is actually our call site, because this cache is like, let's call that, I don't know, link evaluator apparently. That the one? Surprised. Class. Functools. So make link evaluator. This seems to be like I might be attached to the wrong class. Yeah, so this needs to be on the package finder. So let's just add that apparently. Self cache. Okay, so yeah, so self cache disk cache. That's going to be self class name, because I mean, why not? Good enough for now. And this cache itself needs to actually have a platform is imported, and that's going to be user cache dir. That's going to be app name. Well, name, and app author false. Interesting. What does app author say? C platform deals app author. Platform deals app author. The name of the app author or distributing body for this application. Typically, it's the owning company. The default. Okay, you may pass false to disable it. How do other call sites use that? They just say false, apparently. So, okay, so I can just use user cache deal without actually using this one directly. So this is going to be pip internal app deals user cache deal, and we don't need to pass in anything fancy. So this is just going to be app name. Yeah, this is going to be like the thing that we aim for. So we don't need to import the vendor thing ourselves. Anyhow, okay, so we've got ourselves this cache. No new line in the YAML file, that's all right, because we are going to, well, implement everything. So we need to implement get, and we need to implement set, and we need to implement a lot of stuff. So first of all, is this going to return something? Yeah. So self their path. That's going to be that. Is this returning like the returns cache directory tied to the user? That's all right. That's good. So that's going to be cache path. And this is definitely implemented, or we are going to implement that in a minute. So how would we initialize this correctly? This needs to store arbitrary Python objects? No, this is going to be only storing, you know what? Yeah, we can just get bytes. That's a thing. Yeah, so this is apparently init dictionary nothing, and we can either, I don't think I've seen that used in any place like this in a dictionary. So basically, okay, so apparently we are returning either bytes or none for getting and setting things. How would we use that? Interesting. So we could shelf stuff. We could use some other way to maybe Do that. Um, Apparently, are we using message back? Interesting. Is that a thing? Are we actually using message back? I mean, message back is nice. Like I definitely like prefer message back over JSON for storing binary blobs. So let's do that. Apparently. Um, let's just actually look up for message back and see if we actually someone actually uses it. So from message back, import star. That's not good, and message back dumps. So apparently yes. In cache control. Interesting. So serializer. Oh, that's very useful. So how is that going to work? So we don't need to serialize and deserialize. We just need to basically just adhere to the contract of getting and setting bytes from this file, which we might want to actually... okay, so let's do that. So we need a lock because every cache needs a lock at this point because we are reading and writing from a file. And we are probably not allowed to use SQLite. Probably. Doesn't seem like a good idea to use SQLite. So let's actually just... So I really want to like not read the full file every time, but let's just use that because this is still faster than whatever it is. So okay, so let's just self cache. That's going to be self cache path, and that's going to be resolve dot read bytes. Yeah, you know what? Let's just use message back. The hell with that. This is going to be from vendor blah 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 blah. So from pip vendor serializer message back import pack b unpack b should be fine. Or is it dumps and no, it is pack b and unpack b. So why are they not happy? Are they not happy because they just cannot find reference in message pack PYI? So it's only pack B. Interesting. That's not good. How does serialize? What? Unpack loads. Message pack loads. Okay, so loads and dumps definitely exist. So loads, dumps. Yeah, so with self lock, self cache path, make the parents true exist. Okay. And also we can lock with self cache. That's going to be message pack loads of, well, read bytes. That the thing, loads unpack B. Yeah, and that's going to be our write. So with self lock we can just run that, And now we can, with self-lock, get cache key or none. And let's just, yeah, okay, that's good enough for us. And def set, that's going to be the expensive one because we need to either, yeah, we need to update the value, rewrite everything, and that's it, I think. And delete as well, delete. So delete key, that the contract, yeah. So if key in self cache, and that's good. So this basically represents the one source of truth, and this is basically a persisted dictionary cache. We load it once when we read the file on initialization, and then once we are done with it, once we're done loading, we don't need to like do IO at all. And if we get and set, that's going to basically, yeah, okay. So we basically have a persistence, a persistent dictionary cache. So back to our adapter, or not adapter, somewhere within all of this crap. We need to make this work. So adapter, that's not the thing. Anything here? Where is the thing? I just forgot. Where is it? Sources, page candidates, find all candidates. That's all in sources or package finder. So we build responses. So there's one place that we actually instantiate this cache. Okay, awesome. So that's the place. So in package finder. So package finder has the thing. And here, instead of functools LIU cache, not here, not this one, but in get all, or what was it? There was a all candidates. Yeah, persist cache between runs. That's the one. So instead of doing this directly, what we can do now is basically we've got, so candidates is a list of, what was the interface? Installation candidates. Let's just look at that. Compute best candidate. Interesting. So how would we do that correctly? So let's actually define ourselves our own small thing here. So how would we look at that? So find best candidate cached. That's going to be the same thing like with the arguments. So let's actually have these here as well. And best candidate results, that's the same. And let's actually format that because this is ugly. And now we can try to look it up. So first of all, cache key. That's going to be all of these as a string because I think this is going to be just okay. So stir over all of these because it's either both nuns or whatever. Yeah, that should be fine. So self cache get cache key. And that is going to either be the result. If result is none, then self find best candidates and cache set, else return result. Yeah, and now the only problem is, of course, that this result is bytes. So that's going to be bytes, and we need to actually load that into memory correctly. And how would we do that? So this is an object that has, well, nested objects. Of course it does. Um, how would we do that safely? Is there a way to do that safely? Let's think about it. I mean, pickling is like always a solution, but I'm trying to like be moderate with the amount of pickling that are going to do. But you know what? Yeah, fuck that shit. Let's just go with this cache. Let's just use pickle, and then we won't need to worry about anything. But oh, but these are already bytes, so that means someone had to be serializing it for us. Serialize. Load v4 message pack. Interesting. So let's actually look at that a bit more closely. So SERDI version dumps and loads. So in this, let's say adapter, which is within cache control. So we do have our serializer, and we are only passing it to our controller factory, which is cache controller. Then we look at the serializer, and what it does, it either loads something from the cached data, and or it dumps it. And that is very, very simple, and that's not good for us right now because we need to serialize it ourselves. So we need to go back to wherever that was in package finder, and we need also a serializer. So serializer, serializer, that's going to be serializer, and that's going to be from cache control, serializer, sure. And our serializer is going to do stuff because every time we reference self cache, we need to actually deserialize. So if result bytes is not none, is none, that's all right. And if not, dumps, yeah, that's good. And cache set result bytes, else loads. And actually, let's switch these up because we'd like to, first of all, if that fails, try do that. Except serializer, does that throw anything fancy? Raise. Let's actually look at that. So if we look at loads v4, sorry, prepare, so dumps, loads. Oh, so that's not going to work for us because the serializer is actually using specifically something that's like intended for HTTP requests. So we need our own serializer. So that's kind of sucks. So cache control, cache controller, serialize. This is very much not intended to like be within the Python thing. Okay, I think we have gotten far enough. Let's actually try to finish that with like a dirty trick, which is basically with lock, we are going to um, let's continue with shell. So shell open self cache path, and why do we close that? That's not at all making sense. So with lock, with open. So let's actually with lock open as cache self cache cache. Okay, that's very good. And we can just, if not cache, we can initialize that correctly. We don't need to do that. So this is just going to be, oh, so we don't have a root level. I mean, the root level is a dictionary, so it's just okay. So we don't need to do anything fancy here. So yeah, I think this is it. So we can just load this cache correctly. Can we just do that? So can we like dictionary? We can make that into a dictionary. Probably okay. And now we can try and cache get. That's enough. And we can now with lock cache update and not write bytes, but with self lock and self open as cache update. So this cache as actually does not need to adhere to anything fancy. It just needs to be an object, not. This is not a base cache in that sense. So it is object to object. It does not respect the expires thing, so that's all right. And if key in cache with self lock, open as cache and cache update. I mean, this won't work as we expected to because that is only, we need to replace that. We don't need to update that. Interesting. So how do we pop things out of the cache? So out of the, yeah, so let's just pop the key. Basically, I think this should be working. Probably. There are data races here. If you have two pips of the same interpreter running together on the same time, and you are going to be very sad if you have that. Probably. I'm not sure. Not my problem, let's say. Um, I think that is it. By the way, I think this is just going to be, this is going to be better. Let's just, if this in-memory cache drifts from the cache that's within like the disk, then that's okay. Or we can actually, okay, so we can actually update that with our own self cache, and then we can also self underscore cache equals dictionary cache. Yeah, that means that this is, I think, a better transaction because that means we are definitely not drifting from the cache. And if someone from the disk has already opened like this cache for us, actually, you know what? We can actually be fancier here because this does not require a lock. And if maybe cached, that's equal to that. And if maybe cached, we don't need, there is no loads, so just maybe cached, turned. And otherwise, we try that. Yeah, so that means we are, if we have that cache in memory, then we have that result in memory, then we are fine. And if not, then we're trying to actually use the shelf. So that is like saving ourselves a very small read whenever we are trying to get something that's already loaded. So we are doing one load when we're initializing, and then we try to like save the IO for gets, and for sets we are actually opening the thing, updating everything, and then reading everything correctly. And here we are just popping the key from the dictionary. I think this is like okay. Okay, let's fire that up and see if we get errors, and it says that we have fucked up. And package finder. Have I broken this? Probably. So no serializer. And seems like I have just not finished writing things here. So yeah, no bytes. So this is just going to be an object. So we don't need to do anything fancy here. Results, that's just going to be that. And this is going to be, yeah, if results is none, then we are going to find best candidate. And otherwise, we don't need the serialization protocol, and return our self-cache set result, and then else. We are going to say result equals result. Is that a thing? That seems to be like I just could have just used results. And that's going to be results and results here. So it's either going to come from this cache or from this best candidate. And I think that is it, but we are going to flip some things around because we don't want to actually create another function. So let's just do that. So if result is none, do nothing. If result is not none, we can just return the result. Otherwise, we do anything like everything as usual, and then can extract this as candidate and self cache key candidate. Seems like the thing that we aim for. And we can definitely delete this one. And this tuple can be just used directly as the key because, well, actually, you know what? Let's just keep the string key just to be sure everything's fine. Okay, let's fire it up and see if we have errors. Of course we do. Pip subprocess install build dependencies exited with 2. And it says, what does it say? Missing requirement argument name. And let's go for disk cache. And it says that, yeah, and that's definitely not a thing. What now? Negative sized pass to pi bytes from string size. Dict keys. Negative. Ooh, that's not good. Say what now? So this is not working as I expected it to. So let's figure this out. It's line 86, probably. Oh, 103. Interesting. So 103 is this one. So cache update. Mapping. And this is definitely a mutable mapping, right? I mean, this cache is a shell. So this one is dictionary contains get item, set item, del item, close, sync. Ooh, interesting. I can sync that. So has its own cache internally. Interesting. So can I just sync it instead of well closing it open and opening it like every time? That's interesting. So we can basically try and open that. So this is just going to be self cache equals to this, and with self lock self cache sync. And like there is no good way to do this, but def underdel self cache close. This is not a good thing, but sure, let's just go with that. And here we can just run with self cache get key, and we don't need to do anything fancy, so this is just going to be with self lock. And also here with self lock, no actual cache, so it's just going to be self cache update with key value. So this is just going to be, well, no, key, not update. Oh, I see. Equals value. And self cache sync and delete as well. So if key in cache, key pop, and self cache sync. So I think that is it, and I don't think we need to do anything fancy. Oh, we can also like do the same thing where if it's cached, then awesome. Otherwise, let's do self cache sync, then return the key. If it's none, it's none. If it's not, then not. And try sync. And this should now be quite faster on the second run. Let's actually see how many get requests do we got. So let's just print get key, and if it's actually caught, we got. You know what? Let's do. Yeah. So it's either got this one. Okay, so that's going to be hit key, and also if just track that for a minute. So this occurrence only, and that's going to be result. And if he hits and then miss. And let's see. Okay, so we still have a lot of misses. Do we got any hits at all? Hit. No. Interesting. So we only have misses, which means that this cache is not working as we expect it to. Why is that? So first of all, we can actually try and let's just print the cache. So no, not cache path, but cache. Then self cache. And just to be sure everything is working, let's just list the keys. Rise sync. And it says the keys. And it says negative size passed to pi bytes from string. Could not write production log file. So this thing really does not work as we expected to. So I think, ooh, I know why. Of course. Well, this is cache div. And how do we make that into an actual path? Well, we need path of cache_dir and cache_db. And let's actually call that, well, I don't know, name. dot cache. And it says expected stir got path. Stir, whatever. I don't care. Let's just make it work. And it says that it is still not happy. Why is that? And it says cache closed. This cache object has no attribute cache. And why is that? That is just not true. We do have a cache property. DB file name, mod open, blah, 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 blah. Attribute error. Who tried to access that and failed? Package finder.cache, self cache closed. Exception ignored. Well, definitely not ignored. You know what? Let's just let the interpreter shut down and close that for us. And it says no such file or directory with open package finder cache. And well, protocol write back false. So let's actually look at that. Oh, so we need dunder and enter probably. So let's actually with self open as cache. Then we can self cache cache, and then we. Okay, so never mind about. Yeah, this will probably create the cache correctly, but we cannot use that every time. So let's figure this out. So with. How would we make that a little bit cleaner? First of all, we can just use that as cache path and not like worry about anything else. So self cache path going to be that one. No self here. Okay, so with self cache, okay, so let's just, yeah, self cache going to be an empty dictionary with self lock with cache. Dictionary cache should be fine. And let's just move on with all of these. So self cache, and now we can just, and we don't need to sync anything. We can just cache get. And once we have our results, we can go with self cache key result. And also here, self cache key result. So this is our miss. This is one hit. This is going to be hit memory. This is going to be hit disk. And that's going to be self cache get underscore cache. And within this is going to be colon set directly into the cache itself, and then self cache key value, and we can close that quickly. And same thing here. So comma blah 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 blah. Blank go away. we'll see. Key in cache. Yeah, if key in cache, then cache pop, self key, self cache pop. Okay, I think this should be fine. And it still complains about what? And it says no such file or directory. And we do need to do something in the lines of, well, making sure this actually exists. So this is going to be the directory. And we can now make that, so make the whatever we need to do and the directory. And please work. Yeah, okay, so we've got a lot of misses. And we then crash on something else, which is negative sized pass-through keys. And why is that? Because when we call dict on cache, this is basically going to crash apparently. So why does shelve work like that? Flag, protocol, write back. Seems like I'm not happy with shelve that much. Protocol, default protocol. Oh, oh, flag, sorry. What is flag here? Open. DB file name shelf, flag C, dbm open flag, flag R. So what is C? C is for read-write access to a new or existing database. W for read-write access with an existing database. Wait, and C read-write access to a new or existing. Okay, so we do need C because we want to create. N for a read-write access to a new database. So this is new, this is new or existing, that's for an existing. So I think this is correct. Persistent dictionary for reading and writing. Write back. What does write back mean exactly? dbm open. No write back here. Self init. What does write back actually mean? If write back, self cache key. So apparently there is a key, like another cache internally. But that doesn't really matter because we are using a context matcher, which means we're opening and closing everything all the time. What seems to be the problem? So this cache is basically not happy because this is apparently okay. So let's just add self. Okay, so cache and the blah 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 equals to blah 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 blah. Just so we'll have some kind of like data in it, and it still says negative size passed. So dict cache does not work. Can we update dictionary with that? So let's just dictionary and then star star into self cache. Star cache. Right? Is that a thing? And it still will say, yeah, dict keys. Pi bytes from string and size, negative size passed. Ah, that's the default. We don't need that. Cache update self cache. Well, that's not going to be useful at all. Cache sync to be very, very explicit. And it still fails on the same thing. So, okay, no fast path. Let's just use self cache with nothing fancy. So, no need to do any locking or IO here. And here, no fast paths for us. And we just go with self cache get cache key. If result, then awesome, hit and return result. Otherwise, we do nothing. Yeah, nothing. So basically, we just return the result. So yeah, let's just do return result. Oh, but we do want to log if we have hits. Otherwise, okay, so else this. Okay, so that's going to be everything here. And in our set path, we are going to do just this right. And in the delete, we are going to pop. And I think this is a cleaner thing, but probably less performant. Anyhow, okay, so a lot of misses, but hopefully maybe we are, yeah, so this does not look good. But also, like, these hashes objects don't seem to be like good keys. We can actually try and just let's debug that. So cache path going to be that, and cache path read bytes, and let's just print the length of that. So cache size bytes, that's going to be that apparently. Okay, and let's actually run that. That was never closed. Okay, let's run that again. And it will say reusing existing blah 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 blah, and it says no such file or directory. So this definitely does not write anything. So that's not good at all. So that's why we don't have any hits currently. We are statting this, and we definitely follow symlinks. That's a property that, yeah, that's not really defined here. With shelf open as DB. Protocol write back. Okay, so let's try write back through. I mean, this whole shelf thing is like not working as expected. I thought this will cut a lot of time, but apparently not. Persistent dictionary recipe. Definitely. Persistent dict. Oh, wow. Okay, that's quite long. Okay, D shelf open. D key data. Data D key, delete. Close. DBM. Interesting. So can we just use DBM without anything fancy? It's a generic interface variant. So slow but simple implementation of DBM dump will be used. Um, with open cache as C. Um, file. Open the database file. Okay, so I think this is, I mean, like if that won't work, like if using DBM won't work, then we will probably need to do something fancier. So um, let's just do that. Um, uh, let's just do this. So this won't work if cache path does not exist. Cache path touch. Okay, that's good. And DBM. We don't need to do any write backs or anything like that. DBM, DBM. Expected stir bytes got object. So DBM is only for stir strings or bytes, which is kind of a shame. I really wanted something simpler, but still like Pythonistic, sort of. Um, okay, so probably this is not being set correctly. Now that I think about it, we are missing a lot of stuff here. If results is none, return results. Print using cache. Yeah, so this is definitely not working. And it says pip internals hashes object. So this hashes thing is basically not working as we'd expect it to. But this one, let's just actually make sure this is actually working. So print set key. Okay, so we are setting the keys. But does this work? Because if we stack them, they are still 0 bytes small. Where is this? That's actually vent cache directory. Yeah, so this one actually works. So why is that not working as we'd expect it to? So that's .cache.db maybe. Let's try that. And it now says something fancier. DB type could not be determined. DBM. Yeah, so no touch. That's very important. And let's sync that. And if that DB type could not be determined again, then we can basically try to reset that. So with shelf open, it says, yeah, DB type could not be determined. That's very good. Okay, so we can try this again. Apparently, I needed the .db extension here, which is crazy, but sure. So with self flock open, blah 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 blah, and we can try that. If that does not work, that try pass and accept dbm. This is probably a runtime L. What is it? dbm L. Okay, so apparently dbm error. Is that a thing? Apparently yes. Okay, so dbm error, link, open, pass. Yeah, okay, seems fine. And it now says no such file or directory. Package finder. Okay, so cache.db. And it now says self cache, self open, stat. Where do we crash? On the stat thing. Okay, interesting. So let's not stat anything and let's just pretend everything's working for now. And we've got a lot of sets, no hits at the moment. And we are always missing. So this is not working as expected. So these hashes, if we get and set these hashes, we are basically fucked. So cache set, cache key. So what are these hashes? A wrapper that builds multiple hashes at once and checks them against a known good value. So is hash allowed, raised, check against file, has one of, bool equal hash. So they have done their hash and done their equals, which means, oh, but this is not portable because this is hashing against the new Python runtime, which means that this hash is different every time. So that's not good. How do we make these into something that's serializable? About that for a minute. Check against path has one of bool equal. By the way, how big is this hash at this point? This .db is 11 megabytes. So that's kind of working. First of all, we can destroy that. And let's figure this out for a minute. Let's actually go to package finder. So these are all hashed within the runtime, which means these are hashable, kind of, but we are still like not on the right path because we need to hash them between runs, not like intra runs, not intra runs. Anyway, like anyhow, Python hashes are not consistent between runs for a lot of good reasons, and we need to combat that somehow. Let's think about that for a minute. Let's find a trust internet false. How can we serialize this correctly? So these hashes, do they have like a dunder stir or something that's repeatable? No. Has one. Oh, check against path, check against raise. Check against is hash allowed. That's a bool. Digest count. So what is that? Checked links against hashes, matches, checked %s, that's like the amount of candidates for a project. But this one against these many hashes. Not good enough for us. Um, let's figure this out. So we could use the optional dictionary within that as part of our key. So if hashes are not none, then it says for algorithm, algorithm, yeah, dictive algorithm names pointing to a list of allowed hex digests. Okay, so it's sorted, inserted into this dictionary. Interesting. Hex digest, hash allowed against chunks. Not very nice, this whole thing, because I mean, okay, so this is the thing that I want to basically have as my key. Let's actually extract that because apparently we can. So this one, as you can see, this is just a comma joined sorted list of all of these. So the same key would appear exactly the same between runs, not only in the same run. So let's actually have a method that returns that. So that's going to be our, let's actually have that as our wrapper. Flashes. Do we have it on the wrapper? We do not. So why are they annoying then? This is going to be our Dunder wrapper. So hash wrapper self and def Dunder wrapper. That's going to return a string. That's going to be this one. So return, comma join, all of that. And now this one is actually useful as our well, key because it's reproducible between runs. So if we go back to this one, we can just say stir on hashes. And also let's go for specifiers and actually figure these out. Returns the string representation of the specifier. This should be representative of the specifier itself. So let's figure this out. Let's just actually, okay, we are winging everything in here. So this should maybe work. Rising. This should be all misses. And then the next run might be with hits. Yeah, awesome. So, that's a really nice win. So that's not going to be now. Rising should be super quick. That's really nice. Okay. So, we could do probably a lot more than that, but we have something that we know where we'd like to cache things. This is basically the place where we are wasting a lot of time. Let's actually disable all the debug prints and so if result is not none using cache, we can end actually, you know what? If is instance best candidate result, then that's great. Otherwise, nothing, and we can actually else else if result is not none, then self cache delete cache key, and otherwise we can set that. Other prints that we have here, let's find those. So yeah, this one is not useful, so we can just say now return. Okay, our cache is working, and it is reproducible, and everything should be mostly okay with that. DBM error should be fine. Yeah, so with that, we can just we have some basic error handling. Pricing should be super quick now. Counter. Where is our counter now? Resolvers. Yeah, that's us. Counter. Okay, cache directory is still printed for some reason, so prints. Print. Okay, anything else that we are printing right now? Only within Python files. Anything that we changed? Yeah, so no logging here. This is not important. Kinda. Okay, so I think this should basically work now that we are. This cache is not defined because, well, I forgot it. I broke this one. So yeah, let's import that from whatever that thing was. So that was from pip internal cache. Yeah, from pip internal cache, disk cache. Oh, it's not from here. It's from vendor. Sorry. From pip vendor cache control disk cache. Is it not? Where's the sitting? Cache control cache disk cache. Cache import cache. And let's actually PySpy that. And it says again, sudo and okay, so as you can see, this resolution thing has shrank quite a bit. So resolve lib is now not very significant in that area. We do have call subprocess, which actually does something, but that's all right. And like this is a better profiler. Like it's also like actually faster, but that's quite nice. And just to be sure, we can actually remove our cache completely, just um, for the sake of testing everything. So package finder and rerun this profiler. This would take time. We'll have a reference. Yeah, and as you can see, now we've got again our SSL and like networking crap here. And the next time we run that, we don't have that. We just have less running time, which is amazing. So yeah, I hope you enjoyed trying to speed this up. This was a terrible experience, but also like very educational for me. And I will try to figure out how do we actually solve the fact that you cannot trust this cache because it's arbitrary code execution land. And if we find a solution for that, I might consider contributing that back to actually mainline pip, because this would actually speed up the life of every person that's using pip tools and pip itself, like the pip resolver, basically. So I hope you enjoyed that, and I definitely did. And I'll see you in the next one. So bye bye for now.